thank you, everyone. Thanks for the invitation. And today I'm going to talk about the interfaces in percolation, especially for the models in high dimension. Well, I'll concentrate on the dimension 3 more than dimension more than 3, because for the dimension 2 it's well known and the behavior is very well studied. Like for the critical parameters, we have the SLE, we have many results about it. But in 3 dimension, it's quite unknown, and well, I would say it's more difficult. So let's start by the introduction of the models. I will start with the Eisen model. Well, today I will only talk about the finite box that will noted by lambda. That is a finite box in ZD. So we'll take a finite box centered in the origin, and the vertices are noted by x, and the edges are E with endpoints x and y, which is in set of edges E. So the Eisen model is a model with model of spins, which is at every point of the vertices, I will put a spin on the x, which will be either 1 or -1. So sigma is called a configuration, and the probability of sigma at temperature, inverse temperature beta, is proportional to the exponential of beta sum over x, y, every nearest neighbor x, y, and then the product of sigma x, sigma y. So we can imagine that at every point I have a spin which will be either pointed to the upper side or the lower side. And we can easily see that when beta is large, the spins will prefer to be aligned. And at beta equals to 0, the configurations is just a uniform configuration over the space, which is -1 + 1 power of v. Okay, and then let's define the interfaces. This kind of definition is initialized by Dobrushin, a Russian mathematician, physician, and he considered the following things. Let's take the box lambda, and then we'll separate the lambda into two parts. The upper parts could be, and the lower parts are upper part is T and lower part is B. And on the boundary of lambda, the upper parts, I will put only plus spins just outside the box. And lower parts are -1. And then he will study the distribution of the sigma, but we take account the interaction with the boundary. That is, just add one bigger box and rewrite the same things, but we fix the boundary conditions. Okay. So it's a geometric fact that we can find a set of edges, which for each edge of the set, I have +1 and -1 on the 2 endpoints, and then for every path between my set T, between a set T and between a vertex of set T and a vertex of set B, I have to touch this interface. So, you have to take the minimal interface in sense of inclusion to define it. But it's not a difficult thing to define the interface in the case where beta is small, beta is large. Okay. So why is it interesting to study this interface? Actually, in his famous paper in 72, I think, he said that at temperature beta big enough, the interface that I will call E. E is localized around the equator, I would say. That is exactly the plane which cuts my box into two parts, and it's the plane which cuts the box into two sides, and this and which separates the T and B. Okay, it's quite simple as result, but what's more is that the interface with a fluctuation of order log of the size of the box. That is the highest point, which since it's random, the highest point it can be at most of order log of lambda. This has a lot of consequences. For example, the existence of a Gibbs measure, which is not invariant by transition, for those who knows. And so this is the result, which holds for dimension larger than 3. And since then, not many results has been done in this direction, but some conjectures are given. Let's mention two things. The first thing is that what happens when the temperature decreases? When the temperature increases and beta decrease, because it's the inverse. So the conjecture is that there is a beta R, which is called Rothstein transition, such that for beta larger than beta r, we have localization, that is, the interface is around the plane. And for beta smaller, we don't have it. Well, this conjecture is quite difficult because for these parts, we don't even know how to define the interfaces, because at very high temperature, the plus sign and minus, the edges which contain plus and minus will kind of percolate in the box. That is, it can be very close to the edges, so it can be everywhere. So this interface, if we define like this, it will invade all the boxes. So it's quite difficult to define, to see that this kind, if we use the same definition, how do we study the interface? Okay. This is the first thing. And the second thing is we will feel even sillier because, well, this box, okay, I can define it. But if I take a box which is like this and do the same thing, I don't have the interface which is like this. I can't show that in the interface defined in the same way at no temperature is localized around the plane which cuts the box into two parts. And even at 0 temperature, that is beta equals to infinity, we already have some results which says that, well, this can't be the case. So the interface can be like this, and it's not exactly the plane. Okay. That's the two things. So for beta smaller than infinity, we can't say anything. So my work during my PhD was, well, initially not to study these two questions because they are too difficult, but to do some okay. Okay. But to do something different is that if I put a dynamic onto the interfaces, what's the movement of the interface can be? So by studying this, I think we explored a new way of defining interfaces, which might be useful to resolve these two open questions. So let me introduce the new definition of the interface. Let's see it in a dynamical way, and let's start with the easier model, which is the calculation model. So I will still take a box, but I will put calculation by edges in this box. That is, for each edge in E, it can be open with probability P and closed with probability 1 minus P. And then I will do a Markov chain on this calculation which is called dynamical calculation. It's quite simple that I'll call it xt for t in n. That is at at each time t, I will choose a random edge uniformly in a set. Uniformly in a set E that I will call ET. And then I will decide his new configuration by a random variable, bt, which we will guess will be the Bernoulli variable. With parameter p. So at each time I will decide whether it's open or closed with probability p, and independently with from the past. All right. So with this dynamic, we can do a lot of things. And one thing is that we can couple different configurations. So we can couple a configuration we can do a coupling between a configuration which is just a normal percolation and a configuration which has an interface. So in percolation, how do we do it? We still take the part T and B, and we don't want the connection between the T and B. So we start with the empty box. At each time, we take the same edge, that is ET, for example. We use the same ET. But when we decide his new configuration, we have to take account the event, which is the connection between T and B. So at each time, when I want to open an edge, I will check if there's a connection between T and B. If not, I open it. And if by opening this edge, I will create a connection, I will not do it. But I will do it in xt. By this means, I will create a coupling between the process xt and yt, with yt which has no connection between top and bottom, but in xt I have it. And I will write mu, the invariant measure of the couple xt yt. So once we have this coupling, we can define different things. That is, the first thing is what's the interface. So interface at time t will be the set of the edges in E such that x, it is open in x, closed in y. And then another important set that we will define is the set of the pivotal edges. Well, it's better to define it with a join. That is the edges which is connected to the top from one endpoint and connected to the bottom from the other point in the configuration yt. That is the edge. That are the edges that we can't open in our process at the time t. So after these two definitions, what can we say about our result? Is that there is a petit da, which is smaller than p than 1, that for and constant kappa, which is larger than 0, such that for every c bigger than 1, for every p larger than p theta, we have the probability of having an edge of interface which is further than the pivotal edges. With this probability is true, so let me explain it with a small drawing. That we can find a set of random edges in the box, but I don't know where, but I can guess it's around the plane, such that the interface is at most log square of the size lambda from this yellow random set, and then how much time do I have? It's okay. Okay, and then well, I will just explain what can we do with the open conjectures. So that for the first one, for example. First thing is that by using a FK correlation and some classical ways, we can transport this result in either model. And then for the first part is that we can show this kind of localization for all p larger than pc, and to study the delocalization of the interface, we can just but it's important to understand the set of pivotal edges, that if they move a lot when the p is small, we will have the delocalization of the interface, and if not, we will still stay on the plane. And for the second point, we can say that our construction doesn't require the symmetry of the boxes, so it may be more adapted to the tilted boxes. Thank you for your attention. If you have any questions.
Yeah, thanks, Wei. Are there any questions? Anyone? A small question, I know it's late. Okay, right.
So in your definition, you have this, so you chose your edges in a random order, right?
Yeah, uniformly in the...
Yeah, I mean, is that important, or would it change anything if you do some, more non-random exploration or whatever? I mean, is it important that you do it uniformly?
Kind of, yeah, because to have this localization result, you have to control the time that a pivotal edge the time that a interface edge disappear in our process, and this time depends on the way that you choose to remove the open edges. So if you can control this this time, I think you can use other ways of choosing the edges.
I mean, my question is if you could get that better if you did something. Okay.
Probably. So if you have a way to make the interfaces disappear quicker, I think we can maybe remove the square in the log and something like that. But to show the localization and delocalization, I think it's not very important, the power of the log. Okay. And then other.
Okay. If there are no further questions, I think you all want to have coffee now. So let's thank all the speakers of the afternoon again.
Thank you.